All right, so here we go, 7.5. So this is concept 9, and this is the only day we're doing concept 9. This is one concept on its own. Tomorrow will be concept 10. That is one concept on its own. Okay, so solving exponential equations. First thing, we want to isolate the base and the exponents. Okay, we want to be able to get those separate. Change it to log form and solve. Right, so it's going to come into play that we need to be, if they tell me log base 2 of 7, I need to be able to do that either with my calculator or mentally. And the easiest way, and I guess we'll do a quick check to make sure everybody can do these on their calculator, because that is one step. If you can't do these on your calculator, we need to fix that, because we're going to get some that you need to be able to do on your calculator to continue on with the problem. Yes, Tom. They're all set aside right now for the SAT. And so after the SAT, I'll get them back. But yes, but we can still do it without it. Okay. All right. So this first one is what we did real quick on that warm up. And so again, we ended up with log base 15 of 285 equals 3x. Okay. What would we do from here? We wanted to solve this for x. What would we do? Okay, if it was just a mathematical equation, how could we solve that for x? What would be the first thought? I don't have x by itself. How do I get x by itself? Divide by 3. Okay, so I'm going to divide this by 3, and then I'll also divide this by 3. Okay, everybody right now, pick up your calculator and do log base 15 of 285 divided by 3. Okay, so that's another thing. We got to make sure that we. Okay, so this is something we need to know for the. So. All right. Okay. Let's say in log of 15. Okay. So. Okay, so yours only does it log base 10. Yeah, I don't think okay, so I think if you have like the TI 30, you can't do a different base. You can't do log base 15. It only does it as log base 10. Okay, so let's just focus on that. Let's not even divide it by 3 yet. So log base 15 of 285, we have what's called the change of base formula. That lets me change my base to whatever I want, and I can rewrite it anyway. So I could say log base 10 of 285 equals log base 10 of 15. All right, that's the change of base formula. So now I can do it with any calculator that only does log base 10, and it has to be in this order. 285 has to be on top, and then that log base 15 goes on the bottom. Okay, so we're going to rewrite this as log base 10 of 285 divided by log base 10 of 15. All of that divided by 3. And I want to make sure everybody can get this with the correct decimal. Okay, so everybody needs to be punching this in, because if you can't get it, I want to step in and make sure you can get it, because you need to know how to do this. Yes. I'll tell you, it's going to be point something. Okay, it's not bigger. It's not bigger than 1. It's going to be point something. So. Okay, everybody should be getting 0.69, 0.7, somewhere in there. Anybody not? Okay, now is the time to ask me, because you need to do this. Okay, and that's what I know several of you had different calculators, so it's part of figuring out your calculator, but your calculator is a tool. You need to be able to use your calculator. Okay, so work all this out, and we end up with 0.70, 0.69, either one would be fine. Okay, that is what X is going to be. And you can check it. If you did 15 raised to 3 times 0.7, it should get really close to 285. We did some rounding, so it's going to be a decimal in there, but it'll be really close. If you check it and you get 16, you know you did something wrong. All right, so let's continue on. Let's look at this next one. 2 plus 5 raised to the 2x equals 132. So again, we're trying to figure out what that x value is. So this is an algebraic equation. What would we do first to work with this? So we have PEMDAS for our order of operations. Am I going left to right, or am I going right to left? Backwards, okay? Because I am solving. So I want to undo any subtraction. I don't have any subtraction going on. I want to undo any addition, which would be this positive piece. So I'm going to subtract 2 as my first step. So I have 5 raised to the 2x now equals 130. This is that idea of isolating your exponent piece. If you have some additional addition or subtraction or anything going on, we want to get that exponent isolated. Okay. 5 raised to the 2x equals 130. How could I write that as a log? What would be the base of my log function? 5. Okay. So log base 5 of what? 130 equals 2x. Okay. So we got to know or be able to do what log base 5 of 130 is. So am I going to have log base 10 of 5 divided by log base 10 of 130, or the other way around? 130 needs to go on top. So this is log base 10 of 130 divided by log base 10 of 5 equals 2x. So do this fraction in your calculator and divide by 2. Everybody should be doing this for practice, so we're going to make sure that we get the correct number. So don't be a spectator on this. Make sure you're getting the correct number. Okay, who's confident that they got it right? 1.51. Who said that? Cole? I know. Who said that? Oh, count. There you are. Sorry. 1.51 is correct. If you are not getting 1.51, ask me right now, and I will help you. Okay, because you have to be able to do this. Don't be shy. If you're not getting this, we have to get this. Okay, we good? All right, moving on. So let's do another one as a word problem, though. If you buy a car for $11,500 and it depreciates 8% each year, how long will it take to be worth $5,000? So how many years will your car now be worth $5,000? So this is going back to that formula that we talked about, the exponential, and this would be exponential decay because it said it depreciates. So depreciate means it loses value, appreciate would mean it gains value. So depreciates, it's losing value. And so we're going to have the subtraction piece of this. So 1 minus r raised to the t power. And we can already see that t is what we're trying to solve for. So t is in years. T is going to be our unknown. So f of t will be my original amount, 11,500, times 1 minus r, which is 0.08 raised to the t power. So 8% as a decimal, with 2 units to the left, we get a new 0 in front of the 8s. Will be worth 5,000, so we know our equation equals 5,000. So 1 minus 0.08, same as 0.92. So we have an exponential that we need to solve for that unknown exponent. Again, first step, we want to isolate where we only have the base and the exponent alone on one side of the equation. So what do I have to get rid of from this one? I want to get rid of this. So I'm going to divide this out on both sides. $5,000 divided by 11,500. I'll just tell you, we'll leave it as a fraction, 10 over 23 equals 0.92 raised to the t power. I want to write this in log form. So I have to write log base what? What's going to be the base of my log? The base of the log is the same thing as the base of the exponent, which is 0.92. Of what? What's going to go in my parentheses here? This piece 10 divided by 23 equals t. All right, that's why we're writing this from exponential into logarithmic form, so we can set it up. Okay, if I do the stuff on the left and I do it correctly, that is t. So all this stuff over here, change of base tells me log, let's do log base 10 of 10 over 23 divided by log base 10 of 0.92 will equal t. Everybody put this in your calculator because there's fractions on top of a fraction. Make sure you can do this correctly to be able to figure out what t is. What you got? No, not 12. Yeah. So I got approximately 9.99 years. You can round up to 10 years, that'd be fine. So somewhere around there. Okay. So take it piece by piece. Do log, open parentheses, 10 divided by 23, close parentheses, hit enter. Write that decimal down. Log 0.092, get that decimal, write that down. Divide those two numbers that you just wrote down, you should be really close. Okay, I'll even give you some leniency on these because these are approximation ones. Okay, we feeling more comfortable now working with logs in our calculators. Like I said, you have to be able to do this. There's no free pass around it. Okay, just 2 more slides. Okay, now let's go the other direction. If we have a log equation, we can use exponents to solve it. So the same thing, like with exponential equations we were solving, we wanted to isolate the exponent piece. Now we want to isolate the log piece. After we've isolated that log piece where we only have log of something on one side of the equation, then we transform it into an exponential and solve. Okay. All right, so let's do 2 examples here. So log of 4x minus 3 equals 2. So this is from our warm-up. So this is really log base 10, even though the 10's not written there. It is log base 10 of 4x minus 3 equals 2. How could I write this in exponential form? So I have something raised to something equals something. What's going to be my base of my exponent? 10. The base of the log, base of the exponent, they're both called the base for a reason. What is going to be my exponent? 2. So 10 squared equals 4x minus 3. All right, this is a fairly simple equation to solve. So I have 100 equals 4x minus 3. I'm going back to 5th grade, if not before that. All right, we can solve this by adding 3 to each side. So 103 equals 4x. Divide by 4, divide by 4. We end up with 25.75 equals x. So these ones are a little bit easier. We don't have to worry about punching in log stuff. We're going to rewrite it in exponential and go. All right, this one here on the right. Again, we're doing PEMDAS in the reverse order. I have 3 times log base 4 of x plus 5 equals 20. So what am I going to undo first? I have a multiplication and I have an addition going on. What am I going to undo first? Well, there's no subtraction, so I'm going to undo the addition by subtraction. All right, so we have 3 log base 4 of x is now going to be equal to 15. Now I can divide everything by 3. So I have log base 4 of x equals 5. Log base 4 of x equals 5. How do I write that as an exponential? Ethan here, what's my base? Correct. What's my exponent? Correct. So it's just saying 4 to the 5th equals x. We should be able to do that in our calculator. This is one I'd have you do mental math wise. 4 raised to the 5th power in our calculator is 1024. So going from logarithmic form to exponential form, calculation-wise, it's a little bit easier. But we're now all ninjas that we can do from exponential to logs and be able to solve with logs. I lied. I got one more slide. This is the last one. All right. Multiple logarithms, meaning they have more than one in here. And remember, we said we wanted to isolate the log piece first. Well, this is playing off concept 8 test that we just took. Okay, if I have 2 logs that are being added together, I have properties that I can combine that into 1 log. Log of x minus 3 plus log of x. How do I write that as one single log? What do I do with these parts? Sterling, what do I do with these parts? Yes, you do. Okay. If I have two logs that are being added together, I can do what with those? Multiply. Okay. So this really is x times x minus 3 equals 1. And I could rewrite this as log of x squared minus 3x equals 1. I can distribute that through. All right, and then into exponential form. Cole, how can I write this in exponential form? Yep, but that's why I just showing it for visual reference. So that 1 on the right becomes the exponent. Base of the log is the base of my exponent, so it's 10 to the first equals x squared minus 3x. I want to solve this, so if I subtract 10 from both sides, I could say 0 equals x squared minus 3x minus 10. Now I have a quadratic that I want to solve. We can do that. Two numbers that multiply to get negative 10 that add up to be a negative 3. So 5 and 2 are correct. Which one's positive, which one's negative? Okay, so that tells me I have x minus 5, x plus 2. So therefore, what does x equal? So, okay, so x equals 5 and negative 2. Right here. What are extraneous solutions? What's that mean again? Okay. Extraneous solutions come about when we do the algebra. We get solutions that actually may not be a true solution. Okay, so let's do a quick check here. If I put 5 in for x, I have log of 2 plus log of 5. Okay, no problems with that. If I put negative 2 in here, I have log of negative 5. Let's look again at, remember our log graph. We did all this graphing. It looks like this. It crosses at the point 1 comma 0. So if I put in negative 2, it says I'm going to take the log of negative 5 over here. Well, that is not in our domain. Okay? This is not going to happen. This is blank over here. I can only have positive values for logs. So write that in your notes, box it, star it, whatever you got to do. You cannot take a log of a negative number, and even more specifically, you cannot take a log of 0, because remember, y is the horizontal or vertical asymptote. It will never touch the y-axis. It will never touch where x is 0. Okay, so like I said, big star in your notes. Log of a negative number is undefined. Can't do it. Log of 0, can't do it. It has to be a positive number. And so 5 is the only correct one because this becomes negative. If this had been x plus 3, even with this negative 2, it would have worked. Okay, so don't look at it just because this is negative, it failed. It failed when I actually put it back into there because I got log of a negative number. Whew. You thought yesterday was the hard day. Okay, so your homework